Welcome back, y'all. In this example, we're going to look at a second version of reducing a toy matrix involved in a general linear systems problem down to reduced row echelon form by multiplying the entire linear systems equation on the left by a sequence of matrices. One of the major differences in this video is we're going to use some of the foundations that we built in lesson 15, where we did sequences of shear matrices grouped together into Gauss transforms. That work we are going to leverage to do multiple elementary matrix operations via the same multiplication. In order to start this problem, we're going to focus on the left-hand side matrix, which is the matrix you see here. And the first thing we're going to do is recognize that entry 1, 1 has a non-zero value, and we will use that as pivot position 1. Another way to say that is we're going to use that entry to zero out all the subdiagonal entries in column 1. Before we do that, let's use Octave to store this matrix. Written on screen is a command that takes this integer matrix and stores it in memory as the matrix A. I'm not going to read that out loud, but you can follow along if you'd like at home by copying that code. Look carefully at all the symbols. Let's go ahead and run that line of code. When I run it, Octave stores that in memory. Please confirm for yourself that the command that I ran worked well. Now that we have that matrix stored in memory, let's cancel out those subdiagonal elements using 3 shear matrices grouped together into a Gauss transform. That Gauss transform looks like this. We've got the identity matrix with 1s on the diagonal. It's a 4 by 4. And then entries 2, 1, 3, 1, and 4, 1 come from dividing the non-pivot element in that column divided by the pivot element in that column and then slapping a negative. So for example, entry 2, 1, we take entry 2, 1 of the matrix A, divide that by entry 1, 1, the pivot, and then slap a negative. So 2 divided by negative 2 is negative 1. With a negative becomes positive 1. That's why that's positive 1. We discussed those in previous videos. Here in Octave, we see to set L1, first we use the I function, E, Y, E, and this is going to be a 4 by 4 matrix. That line of code right there produces the identity matrix with 4 rows and 4 columns. The next thing we're going to do is to set the entries in positions 2, 3, and 4 in column 1. So here we're using index notation. That matrix right here, look, right, 2, 3, and 4 is going to be the column vector 1, negative 1, 1, which is exactly what I have stored there. When I execute that code, I see that L1 is the matrix that I want on screen. Next thing I can do is actually execute that multiplication, L1 times A. Let's go ahead and look. Claim all of these subdiagonal elements should go to 0. Ding, 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 ding. We got it. The subdiagonal elements in column 1 or pivot column 1 indeed went to 0. Notice that pivot column 2 is not in regular column 2, it's actually in column 3. We might have guessed that information immediately by noting that the second column is actually linearly dependent on the first column. If I multiply the first column by negative 1/2, I get the second column for free, which means that the second column has no new information, which means there's no way on earth that entry 2, 2 will be a pivot. Now that we're down to the first set of reductions that happened with 3 shear matrices, we see that the second pivot position is in entry 2, 3, and we're going to use that pivot position to cancel out all subdiagonal entries in that column. To do that, we're going to use a sequence of shear matrices, which again we group together and call a Gauss transform. That is an identity matrix 4 by 4, and then the second column in entries 3, 2, and 4, 2 will have non-zero scalars defined by the negative ratio of the sub-pivot elements divided by the pivot. What I mean by that is negative 2 divided by 6 is negative 1/3, and then I'm going to slap a negative on that and it becomes positive, that entry is positive 1/3. Negative 8 divided by 6 is negative 4/3. If you want more information, take a look at the work that we did in lessons 10, 11, and 12, and also some of the practice that we did in lesson 15 of this course. Here on screen, we see that in order to store this Gauss transform in memory, we'll call that L2. We're going to first use the I function, which sets the 4x4 identity matrix, all zeros except for the main diagonal entries, which are 1. And then we're going to fill out the 2 entries, so the third and fourth rows in column 2, get the column vector 1/3 and negative 4/3. When I hit this, indeed you see on screen that matrix is now stored in L2, and then I can multiply L2 by L1 by A. And if I've done my work well, I expect the sub-pivot elements in column 3 to disappear. What we see is that indeed the 2 entries under the second pivot turn to 0. Not only do we notice that we've zeroed out the proper entries, but we also notice that columns 4 and 5 are actually linear combinations of columns 3 and 1, meaning that in the first 5 columns, I only have 2 linearly independent columns, and I have 3 linearly dependent columns looking backwards. That's the benefit of the stair-step structure. It tells me how future columns are dependent or not dependent on past columns. Column 2 is dependent on column 1. Column 3 is linearly independent from columns 1 and 2. Column 4 is dependent on columns 3 and 1. And column 5 is dependent also on 3 and 1. The next thing we're going to do is identify the third pivot in column 6 and use that pivot to cancel out the sub-diagonal element. Here, this is actually a pure shear matrix. We only need one transformation, still a Gauss transform as well. All shear matrices are Gauss transforms. Not all Gauss transforms are shear matrices. I have the entry 2 in position 4, 3 because 2 divided by negative 1 times negative 2 is a positive 2. On screen here, you see I am setting the third Gauss transform to be the identity matrix with all 1s on the main diagonal, and then the entry in position 4, 3 gets 2. Now I multiply this matrix that I had, which was L2 times L1 times A, by L3, and I suppose that that last entry goes to 0. That's exactly what we get here. The last entry under the third pivot went to 0, but so did the entry after that. What this tells me is that the fourth row of this matrix was actually linearly dependent on the first 3 rows. There's no new information being added because there's no pivot there. Notice also that we have this matrix in row echelon form. And we're going to transfer it into reduced row echelon form, which means we're going to get all of the pivots to a positive 1 value and then cancel out all other entries in each pivot column. Let's begin that process by turning each of the pivots into 1 using a sequence of dilation matrices that we're going to group together and just call the matrix D for diagonal. Here, we need to multiply by negative 1/2 the entire first row so that that turns to 1. The second row we're going to multiply by 1/6, and the third row we're going to multiply by negative 1. Each of those will turn those pivots to 1. On screen, you see we're going to define a diagonal matrix with 1s all on the diagonal. And then I'm going to overwrite entry 1, 1 with the value negative 0.5. I'm going to overwrite entry 2, 2 with the value 1/6. And I'm going to overwrite entry 3, 3 with the value negative 1. Let's go ahead and store that matrix. Now when we multiply D by the matrix that we have in row echelon form, all of those pivots should have value 1. And that's exactly what we see in our calculator and on screen. Now that our row echelon form has pivot values equal to 1, we are going to cancel out all super diagonal elements, all the non-zero elements above the pivots. And here we're going to use the same idea of shear matrices, except instead of downward facing, those shear matrices would be upward facing. Remember that in the forward direction, we actually started with column 1, then we went column 2, column 3, to the right so that there weren't cross-pollinations in cancellations. In this case, we're going to start with the rightmost pivot and work to the left so that we don't get cross-pollination, so that when we zero out an element, we don't reintroduce a non-zero into that element. With that in mind, the first Gauss transform, which is a product of two shear matrices we're going to use, is to identify values of this pivot that cancel out those in linear combinations with the rows. Same process works. We take this non-pivot element, divide it by that pivot element, and slap a negative. 1 divided by 1 with a negative on it is -1. -1 divided by 1 with a negative on it is +1. On screen, you see that we're defining a fourth Gauss transform to be an identity matrix. And then we're going to set rows 1 and 2 in column 3 to have the values 1, -1. Using this matrix, let's go ahead and execute that multiplication, claim these two elements should go to 0. That's exactly what I get. Now I have a single pivot in that 6th column. Next thing I'm going to do, and in fact the last thing I'm going to do, is to cancel out all non-pivot elements in pivot column 2. To do that, I need a single shear matrix, which I'll call L5. To define L5 in Octave, we say L5 is the 4x4 identity matrix, and entry 1, 2 is equal to the non-pivot element divided by the pivot element with a negative. So -2 divided by 1 times -1 is +2. We see that on screen there. Now let's multiply the entire sequence by A, and we see that we get down to the reduced row echelon form of this matrix with each pivot value exactly equal to 1, a single pivot in each pivot column, and all other entries equal to 0. And then the non-pivot columns expose the exact linear combinations used to generate the non-pivot information from previous pivot information. We'll talk more about that in the next lesson. What we've done here is use this sequence of products, as seen previously, to transform A into U. Here's the kicker. Let's define a new matrix E, which is the product of the matrices L5, L4, D, L3, L2, and L1 in that order. In fact, on screen, that's what I'm going to do. Let me go ahead and push enter. This matrix E is going to be a product of Gauss transforms and diagonal matrix, but more importantly, a product of elementary matrices. Challenge for the viewer, decompose each of those matrices into the proper elementary matrices. Once I do this, I'm going to claim that I could take that matrix E, multiply by A, and I would immediately get that matrix into RREF form. Moreover, if I store the vector B, which is done on screen, and then multiply E times B, I get the vector Y. Y equals E times B. This is the same vector that I would get out if I took the RREF of the augmented matrix A, B. When I look at that last row, -1, 3, -2, check that out. Y, which is E times B, was -1, 3, -2. The last entry is numerical round-off error. E to the -15 is about 0, so we could assume that that's 0. This happens in exact arithmetic by the way that we did it. But the point of the matter, though, is that we've translated A into RREF form using a sequence of matrices. Those sequence of matrices brought together are a single product of invertible matrices that we call E, and that allows us to translate our original problem into this problem. With the magic of elementary matrices, we've transformed AX equal B into UX equal Y, and the next lesson is all about how the two solution sets, the two complete solutions to these problems, are identical. They're the same. In other words, solving the AX equal B is the same solution. I will get the same output if I solve the UX equal Y. UX equal Y is a much more beautiful problem algebraically. As always, I would say, don't take my word for it. In the next lesson, we'll discover why that's the case. I'll see you there.